Alright, so this is going to be a two-part problem. We have constant acceleration up a ramp that's inclined 18 degrees above the horizontal, and we have free fall. So we're definitely going to have to split this into parts. Let me draw a quick diagram that explains what's going on here. So we've got a ramp that's inclined 18 degrees above the horizontal. Car starts at the bottom of the ramp from rest and goes up the ramp. And then the car takes off from the ramp. It has some final velocity at the end of part 1 that is equal to the initial velocity at the beginning of part 2. That initial velocity vector will also be 18 degrees above the horizontal. And the car is going to follow some kind of ballistic trajectory and hit the ground. Alright, so let me write down what we know for the ramp and for the free fall part. Now, for the motion along the ramp, I'm not going to split this up into x and y. I'm just going to use a coordinate system that is parallel and perpendicular to the ramp, where up the ramp is positive. And then over here in free fall, I'm going to use this sign convention, where the acceleration is 9.8 meters per second squared, directed downward. Okay, so along the ramp, if we are using the coordinate system that's parallel to the ramp, we're given that the distance that the car travels along the ramp is 25 meters. We're also told that the car starts at rest. We don't know the final velocity, we don't know the acceleration, and we don't know the time. So we're kind of stuck there. For the free fall part, this is the part that goes from the ramp to the ground. So let's see. We know that the acceleration is negative 9.8, and we know the time is 2.3 seconds. Now there is one more thing that we can say, which is that from this point down to the ground, the car has a delta y and a delta x, right? And actually I can find that delta y. If I've got a ramp that's 25 meters long, makes an 18-degree angle with the horizontal, then I can find the height of the ramp. That's the height of the ramp is h here. That's 25 sine 18, which is 7.725. Therefore, in the free fall part, the y displacement is minus 7.725. Right? So remember that these four quantities in our equations, in our assumptions here, they're all vectors. They all have magnitude and direction. The magnitude of the y displacement is 7.7225. Action is downward. The magnitude of the acceleration is 9.8 meters per second squared. The direction is downward. So that negative sign is important. Okay, so for free fall at least, we've got 3 of our 5 quantities. So I can solve for the other 2. Right? I can solve for v0y and vy. Now I haven't bothered for the free fall part to talk about the delta x, the x component. I'm not writing down delta x or calculating delta x or worried about delta x, because the problem doesn't care about the delta x. So if I solve for my unknowns in delta y, I can use delta y is equal to v0 yt plus 1/2 at squared c. If I go through and solve this, I get 18.20 is equal to v0 y times 2.3, and so v0 y is equal to 7.9 meters per second. Alright, so now let's go back up here and revisit what's happening at the top of the ramp. We have a v0. This is for part 2 of the motion, remember. We have an initial velocity that is directed 18 degrees above the horizontal, and we know now that the y component of that initial velocity is 7.9. Well, that means I can solve with hypotenuse, right? I can use the identity that sine of 18 is equal to opposite over hypotenuse, which is 7.9 over v naught. So v naught is equal to 7.9 over sine 18, which is 25.6 meters per second. So the magnitude and direction of the car's velocity, the instant after it leaves the ramp, has a magnitude of 25.6 and a direction that is 18 degrees above plus x. Okay? Now remember too that that's the final velocity for part 1, right? So for part 1, v is 25.6. So we can plug that back in up here, right? Well, now I know 3 out of my 5 quantities for the ramp, so I can find part B, which is the acceleration along the ramp. I can use the equation that doesn't have t in it. I guess I should use delta S here. Alright, so that's 25.6 is equal to 2 times a times 25. And so that gives me my acceleration along the ramp of 13 meters per second squared. And I'm done. Now, I want you to realize that this problem is just the reverse of some problems that you've seen before. Imagine, for example, that you had been given the final velocity at the end of the ramp, or the initial velocity coming off the ramp. You could have turned that into a time, right? Or if you're given the time, you could have turned that into a delta y. All we're doing is the reverse. A similar problem to this is the Puma problem from the books, chapter 3. So this is a tough one, a tricky one, and it takes some practice to learn how to do these kinds of problems and know what to do. So you may want to review this and try it again on your own later.